In this lecture, I'll introduce the base namespace of BADA. First, I'll explain the fundamental base class of all BADA classes, the object class, and the frequently used string classes, along with a few BADA wrapper classes for C++ data types. After that, I'll explain the buffer and date-time related classes. The base namespace contains all the fundamental classes and interfaces around which the entire BADA system is built. It forms the basis of BADA. All BADA classes are derived from the object class, which is a part of the base namespace. This namespace is designed to be efficient and reliable, since the functionality of all the other namespaces depends on it in some way. It also contains classes that encapsulate primitive types and interfaces, which are abstract classes that provide generic functionality. I'll start with the base class of all BADA classes, which is the object class. The most fundamental class of the base namespace is the object class. The object class is the base class of all BADA classes, except those with static methods only. The object class provides the equal and getHashCode functions. The equal function returns true if two objects are the same. The getHashCode function returns the address of the object in the current implementation. In the base namespace, the wrapper classes for C++ types are implemented, namely Boolean, int8, short, character, integer, long, long, float, and double floating point. Additionally, the string, buffer, and byte buffer types have been implemented so that they can be used for arrays. Also, the datetime, time span, and UUID types have been implemented. Let's have a look at the string type in more detail. Basically, in BADA, a string is a sequence of Unicode characters. The content and length of the sequence can be changed. So if a string is created without specifications, 16 bytes are allocated by default. After that, if the string length is changed, as much as 1.5 times the actually required memory is allocated. The maximum length of a string is 2 to the 32nd power minus 1 bytes. The primitive functions provided for the string class include functions to clear the string and to identify whether the string is empty, such as the clear and isEmpty functions. In addition, the getCapacity function can be used to get the size of the allocated memory, and the ensureCapacity and setCapacity functions can be used to set the capacity of a string. Also, the getLength and setLength functions to acquire and set the length of the actual string are provided. Now, to use a string, you first have to initialize the string. You can initialize a string with an existing ASCII string or Unicode string. In addition, if you want to create a string with a capacity greater than 16 bytes, you can create a string by specifying the required capacity. Now, I'll explain the string functions that can be used to acquire a character pointer or character. As described previously, since a string is basically a Unicode character sequence, you can handle a string as an mchar type that is used to save Unicode characters. For example, I declared an mchar type variable ch and created the string using a C string made with an ASCII string, ASCII string. Here, I retrieved the 7th character using the bracket operator, and the character S is saved in the variable ch. You can use the getChar@at function to perform the same functionality as the bracket operator. The getPointer function is used to acquire the mchar pointer to the string. To change a character in a string, you can use setChar@at or the bracket operator. In addition, the format function is provided that corresponds to the sprintf function in the conventional C language. The first parameter specifies the maximum length of the string. The other parameters are the same as those of the sprintf function. In addition, you can assign a string to another string. The operators plus equal and plus are provided to allow appending a string to another string. In addition, an append function is provided, which can also be used to append a string to another string or to convert an integer value or a floating point type into a string type and append the converted string to a string. In this example, I've created a string containing 10 plus 10. I appended the equals string to the string using the operator plus equal, and appended an integer type value to the string to complete the numeric expression. In addition, you can perform a binary plus operation for a string. The insert function can be used to insert a string into the middle of a string. The usage of this function is the same as that of the append function. Functions to handle substrings within a string are also provided. First, you can use the substring function to acquire a substring from a string. You can use the replace function to replace a substring with another substring. You can replace a substring with another substring by specifying the substring to be replaced as the first parameter and the new string required as the second parameter. The remove function enables removing a substring from a string. Functions to compare the contents of strings are provided, such as the compare to, equals, starts with, and ends with functions. In addition, the index of and last index of functions can be used to identify if a string contains a specific substring or to find the position of a substring within a string. The to lowercase and to uppercase functions can be used to change the characters of a string to upper or lowercase characters. The reverse function can be used to reverse the order of the characters of a string. This example illustrates how to modify the contents of a string by using various string functions. First, I created a string, and changed the first character of the string to the capital letter A. Printing the result will display a string on the screen. After that, I appended a substring, is cool, to the string using the append function. As a result, the string has been changed to a string is cool. After that, I inserted a substring class into the 9th character position of the string. The substring class is inserted between string and is. As a result, the string has been changed to a string class is cool. Then, I called a function to remove 2 characters from the first character position. It removes the A and the blank space. After that, I inserted the into the first character position using the insert function, and the string became the string class is cool. After that, I created another new string. I initialized this string using the format function. The initialized string is 5 plus 2 is. Then, I appended an integer type constant 3 to the string. Then, I called the index of function to acquire the index of the plus character in the string and changed the character to minus. Then, I found the is substring and replaced it with equals. As a result, the str2 string becomes 5 minus 2 equals 3. The last statement appends str2 to the str using the operator plus equals. In the next few slides, I'll explain Bada's buffer class. Although in general, the buffer class is similar to an array, the class performs the role of the buffer using the internal values of the position, limit, remaining, mark, and capacity because it's been designed as a buffer. We'll look at each of these in detail. First, the position is the value that remembers the position where the data was written to or read from in the buffer array from the last operation. Therefore, if the read or write operation is performed in the buffer, the position value saves the position at which to read or write the next time. The limit value represents the last position in the buffer where meaningful data is written. The remaining value represents the amount of remaining data space. That is, the remaining value represents the difference between the position and the limit values. The mark value is the position in the buffer specified by the user for an operation. Users can move the position to the position indicated by the mark value. The capacity value represents the maximum capacity of data the buffer can hold. To actually use a buffer, you don't need to use the buffer itself, but the buffers implemented for each specific type. Okay, let's have a look at the basic operations of the buffer. First, the set position function is used to set the position value to a specific position in the buffer. The rewind function is used to move the position value to the beginning of the buffer to perform the read or write operation again. The flip function moves the limit to the current position and sets the position to 0. The flip function can be used when you have written data to the buffer and you're about to read the data from the buffer. For example, if writing to the buffer is completed, the buffer's position value would indicate the end of the data within the buffer. At this time, if you call the flip function, the limit is set to the position indicating the end of meaningful data, and the position is returned to the beginning of the data in the buffer to prepare for the reading operation. As I mentioned before, the reset function is used to move the position to the location indicated by the marker. Besides these functions, functions to get the memory size, limit, mark, and position of the buffer, functions to get the length of the currently remaining meaningful data, and functions to identify whether there's remaining data are all provided. Additionally, functions to explicitly specify the limit, mark, and position values are also provided. The following functions to read or write to the buffer are provided. The get and set functions get and set data at the current position and then move the position accordingly. To get or set data regardless of the current position, the absolute function and the bracket operation are supported. Additionally, functions to save data in the C array type and directly get the C array pointer are supported. Also, a read from function is available. The read from function is used to read data from the buffer and is generally used to copy data from a relatively large buffer to a small buffer. Besides these functions, the functions and operators to compare the data of buffers are provided. Let's have a look at an example of using a buffer. First, we have to initialize the buffer. We've declared an integer buffer and defined the buffer size using the construct function of the buffer. Then, we've set the buffer with the C array data by calling the set array function. The flip function is called to read the data from the beginning of the buffer because the set array operation would have set the position to the end of the valid data. After this, we get the data in sequence by calling the get function of the buffer using a loop until there's no remaining data in the buffer. As mentioned earlier, since the get function moves the position one by one whenever it reads data, we can read the data in the buffer sequentially. Then, I've set the position of the buffer to 6 and set the length of buffer 2 to 2. Now, if I read the data from the buffer to buffer 2, since the position of the buffer is set to 6, the 2 elements after the 6th element will be read. After this operation, 7 and 8 will be in buffer 2. If I rewind the buffer and read it again, 9 and 10 will be added to buffer 2. As you can see, you can conveniently use the buffer to record and read data in an array sequentially. In the next few slides, I'll explain BADA's date and time related classes. The base namespace provides two classes for date and time related operations, the datetime and time span classes. The datetime class is used to represent the absolute time, and the time span class is used to represent the time difference between two time values. The value returned by the time span is in milliseconds. In the datetime class, functions to add the time span, years, months, days, hours, minutes, and seconds are provided, and the functions and operators to compare the date time are provided. Additionally, functions to set or get each of the properties are provided. A function to return how much time has passed since the minimum value of the date time as a time span value, and a function to return how much time has passed since midnight of a day as a time span value are all provided. Besides these functions, functions to convert the current date and time into strings, to identify whether this year is a leap year or not, to find the day corresponding to a date, and to get the date time from a string are provided. The time span class provides functions to represent a time span in days, hours, minutes, and seconds. Functions and operators to compare two time span values are also available. And of course, you can add or subtract time span values. Additionally, a duration function to get absolute values from a time span value and the negate function to negate a time span value are provided. In the next slide, I'll explain the UUID class. The OSP base namespace provides the UUID class used to represent a universally unique identifier. The UUID structure consists of 32 hexadecimal digits displayed in 5 groups separated by hyphens to form a total of 36 characters, 32 digits, and 4 dashes. The 5 groups in the UUID structure is represented as 8-4-4-4-12, with each number representing the number of hexadecimal digits in the group. Functions are provided to identify whether two UUID values are the same, to convert a UUID into a string, and to convert a string into a UUID, and to convert a string into a UUID value. Now, let's summarize this lecture. First, the object class is the base class of all BADA classes. The base namespace provides various type classes to wrap C types. BADA provides its own classes for handling string, buffer, and datetime related operations.